Hello everyone, welcome to the lecture on ProCACD, and this is a part of the process modeling course. And if you have any questions or doubts in the later stages, please feel free to contact me. And for your convenience, I have also added the notes for the presentation in the below, so you can also go through it if you're not able to follow me in the class. Okay. So in this lecture, I will walk you through a tool called as ProCACD. Okay, so which can be used to solve different problems related to process design, controller analysis, etc. So in this lecture, first I will give some background information about processes and why do we need to control these processes and what are the different control systems we have, etc. And this background information, I'll just limit it to the overview of the basics so that some of the terminology will be used later in the lecture. Okay, so the lecture is pretty much similar to the pattern what we have followed previously, where in the first half I will go walk you through the slides and by giving you some examples and showing you the screenshots of the tool, etc. And in the later half of the class, what I'm going to do is I will give you a live demonstration of the tool where I'll pick a problem which we have discussed in the class, and then we'll try to kind of formulate right from the beginning, and then we'll try to solve it, and we'll also try to analyze the results and see what can be concluded from the results. Okay, now let's go and start with what is a process and why do we need to control it. Okay, in general, a process consists of individual units which are interconnected with one another in a systematic manner. Okay, in every stage, in every intermediate stage, it consumes one or more types of resources. I mean, it can be energy, materials, machines, time, money, etc. Okay, which converts the inputs to the outputs of that particular stage. Okay, and this continues until a known goal or an end result is reached. Okay, so when I say process, I mean process can be like a complicated processes like oil refining process or a simple online shopping process also. Now let us see a very simple example on process, and we'll try to kind of see how it goes. Okay, so we all generally buy goods online, right? I mean, the whole process can be divided into 4 interconnected steps. Okay, so in step 1, the consumer or the customer, he generally goes online, he opens the product catalog, what are the products available, and then he goes searching with all the products, and if he finds a product which he likes, he orders it, right? That's the step 1. Once he places the order, it goes to step 2, which is the sales and finance. So what this step does is like it tries to verify with whether the user had a successful payment process or not. So once the payment is successful, the product information from the sales and the finance will go to the inventory to retrieve that particular product. Okay, now once the product is retrieved from the inventory, okay, it goes to the shipping process where that particular product is packed and shipped to the address of the customer who has ordered. Now you can see how the intermediate steps are kind of interconnected, and the output of one acts as an input to other. And also you should be very careful that the resources used at different intervals or different intermediate steps are different. Okay, they can be same, but they can be also different. So that is one important thing you need to really understand. Okay, and I just gave a very simple example for your understanding, but then there are processes which are very complex where the intermediate units can run up to tens of hundreds of intermediate units or interconnected units. Okay, now that we have learned what is a process, and let's see what is process control and why do we need it and what advantages does it bring to us. Okay, now we all know that process control is a very important aspect in any industry. Okay, so in easy terms, process control tries to regulate all the aspects of the process. Okay, and this is very important when dealing with a process or a product industry. So what are the main objectives, let's see, of a process control? First and the foremost thing is the process control methods or strategies are generally used to reduce variation in product quality and maintain the product consistency through the production cycle. Because if you take a continuous process, the production units generally run over years together. Any production facility generally has a lifespan of 15 to 20 years. And of course, there is a maintenance after every specific time period. But then the production process generally runs at least for 1 year without any major interruption. So the product quality and consistency on the day one has to be the same on day 30 or day 300 or day 365. Okay, so that is very important, and this is very important when you're trying to produce a medicine, because it's absolutely necessary that you want to have the medicine composition and physical characteristics to be the same over the different production cycles and with the prescribed amount. Okay, or else this would be used by public or people, right? And this can be catastrophic. This can cause a lot of problems. Okay, so what is the other important advantage of having these process control strategies? So these control methods are used for product and process safety. For example, if the reactor temperature is not maintained properly, it may lead to reactor failure, or it may also lead to decomposition of the product because the temperature of the reactor is not maintained and the temperature was rising, and it might cause the product to decompose because of high temperatures. And other important areas where the control structures or control methods will be helpful is in reducing the waste and improving the efficiency of the process. And this will overall help in reducing the manufacturing costs and improve the environmental performance of the whole process itself. Okay, of course these control strategies can also be used for process optimization. Okay, now that we understood the basics of process control, let's see what are the different types of control systems. And generally, this is on a very broad level classification. These control systems are classified as open loop and closed loop control system. Okay, in an open loop system, there is no feedback to the controller. I can give examples of an open loop from our day-to-day life. Okay, an automatic dishwasher or an automatic water sprinkler system. Here you can see that even if the dishes are dirty after washing, the machine stops after a prefixed time, and because it doesn't get any feedback from the output dishes. Okay, that is exactly which is rectified in the. So in the closed loop system, the output measured variable is measured and is compared to the desired variable, and based upon this difference between the desired value, or which we call a set point, and then the actual value which is getting from the sensors from the output of the process, the control action is decided. Okay, so in this way you should know that you can easily know whether to increase or decrease, let's say, the temperature of the reactor, or let's say the flow rate of an heat exchanger, etc. Okay, now let us go um, to see how these open loop and closed loop systems work on an kind of an live example. Okay, so we all eat chips, right? I mean, does anyone know how the potato chips are made? Okay, I mean, it's a fairly straightforward, simple process. Okay, so in the production of chips, okay, first the potatoes are bought, they're washed thoroughly in water, and they're sliced and they're dried to remove the excess water. Okay, so before they're fried, I mean, of course, the last step is the frying step. Now, it is very important to control the water content present in the dried chips, or else it will create a huge problems in the fryer. Okay, so let's see what happens if we keep an open loop system on such kind of process. Okay, so in this kind of open loop system, which is like there's a set time based upon which the chips are heated using the heating elements, which means there's a prefix time, let's say 10 minutes for a batch of 100 kgs, let's say. The controller is fixed and the controller has a fixed time, and for this particular 10 minutes all the heating elements would be passing all the heat to the potato chips of 100 kgs. Okay, now just think about this. Different batches in general requires different times because the water in the chips can vary, and the potatoes size, the slices and everything also has effect on the amount of water it has or it absorbs. So keeping a fixed time is not a ideal situation in this kind of process. Also consider this if there is any disturbance in the heating elements. Since these are uh, equipment equipments or tend to go or decrease their efficiency over time. Let's say these heating elements over the time had fouled over the surfaces, and the amount of heat it is kind of sending in the potato chips over the time has reduced, let's say. So that is one of the disturbances caused in the heating elements. Let's say a similar kind of disturbance was there in the potato chips itself, where let's say now the a fresh batch of potato chips were bought, which has a higher capacity with respect to absorbing the water. In that case, taking these two into consideration, the amount of time has to be increased, but then the controller doesn't know at this point of time, right? Since or even during the process or even after the process, because it doesn't have any feedback coming back to the controller. And now consider the same thing in a closed loop. Okay, so in the closed loop we'll have a sensor engine on the dried chips coming out at the last process step. Okay, here the sensor will take the water content from the chips and it will send back this value to the controller. Now we all we all we always have the desired water content, right, which is our set point value for the chips. Now this value, the sensor value, is compared against this set point, and based upon the error the controller decides whether to increase the heat or to decrease the heat to match the set point, which set point of the water content in the dried chips. Okay, so you can see that the advantages of a closed loop system or open loop system, especially where there is some sort of disturbances in the process. Okay, Now let's go and see how ProCACD can be used to solve different problems in process design, controller design, or even process analysis, etc. Okay, so I'll just give some brief introduction about the tool. So this is how the interface of the tool looks like. Okay, so the tool or the platform was developed entirely in C Sharp, and it was developed at JGU, at JGU by our own research group. Okay, and the acronym CACD stands for Computer Aided Controller Design. Okay, now let's see what are the different problems it can solve and what is the overall architecture of the tool. Okay, so this slide gives you the overall architecture of the platform, but the most important thing that you need to understand is the different types of problems that it can be solved using the platform. So if you see the architecture, you could see it has design methods where we have design methods to design a controller, or it also has design methods to design both a process and a controller, or it has options where you can just run simulations like dynamic simulation. Okay, or you can just do analysis if you're not interested in designing. If you just want to analyze, let's say, your controller performance, you already have your control structure, your tune parameters, and all you need to know the performance of this controller, you can also do that. Okay, or if you want to test different manipulated and control variable pairs like controller pairing, you can also do an analysis using ProCACD and decide which pair is the best. Okay, so also the tool has access to the modeling tool, the MOT, the model testbed, and the model libraries, which can be configured automatically to represent different types of problems. Okay, first I'll show you how to develop a generic model that can be used for, let's say, controller design, analysis, or just for simulation. So that is very important because you don't need to spend time in the MOT to develop a model that could only just run, let's say, controller design problem or an analysis problem. If you can come up with a generic structure, then the same model can be used to solve different problems of the same system. Okay, so here we will try to see how to do that. Okay, so as I previously mentioned, the modeling requirements for ProCACD is taken care by MOT, the modeling test bed, okay, which is very well integrated. Okay, so the basic idea of a generic model is, since ProCACD can handle different types of problems from simulation, design to analysis, we will build only one model, just one model that can be used for all the problems mentioned above. Okay, so for this, we will use the help of binary variables and also some fixed naming conventions. Okay, so I will explain in detail. I will also take an example and we will try to kind of develop the model in a generic way and see how this can be used in solving different problems in ProCACD. Okay, so for this, we'll take a very simple example of tank model, okay, which has one inlet and one outlet. The inlet flow rate and the outlet flow rates, let's say, are defined as F in and F out. And A is the cross-sectional area of the tank. The outlet of the tank is equipped with valve, which can be used to control the height of the liquid. Okay, and now the system equations are as follows. As you can see, the height of the liquid in the tank it varies with time, and you can see it's a function of both the flow rate in F in and F out, and also the cross-sectional area of the tank. Okay, similarly, F out, the flow rate coming out of the tank, is a function of the valve opening, which is represented by alpha, and then the height of the tank, the height of the liquid in the tank. Okay, now let's say HSP is the set point or the desired value of the height of the liquid in the tank. Then the error is the actual value H minus the set point. Okay, now alpha is the valve opening. Let's say I want to write equation for a proportional controller. So the alpha is given by proportionally constant P1 into error plus the alpha star. Okay, so let's say this is the system, but then if you clearly see, this can only be used for let's say closed loop simulation with proportional integral. Okay, it cannot be used for a different structure of, let's say, PID. It cannot be used, or it cannot be used for let's say open loop simulation also, or it cannot even do simple analysis also. So that is, now I'll show you how this kind of system can be developed in a more generic way. Okay, now just remember about this kind of suffixes, and I'll tell you why it is very important to write these suffixes. So all the manipulated variables in the system has to be ending by MV, and similarly all the control variables in the system has to end by CV, and OL represents the open loop binary variable and CL represents the closed loop binary variable. Okay, now if you convert the same system of equations into a more generic way, this is how it will look like. Okay, you can see, since H, or the height of the liquid, is the control variable, we have appended CV to the variable H, and we also appended 1, which represent its one variable. Okay, if you have a second control variable, then it will be represented as CV2, and similarly for a second manipulated variable, it will be MV2. Okay, now you can see the second equation in a generic format will have MV1 for alpha and CV1 for the H. Okay, and the third equation, error, you can see you have added SP, which is for the set point. Okay, and CV is for the control variable 1. Okay, now the most important difference would be in the control equation. Now just please follow very carefully here. So here alpha, which is a manipulated variable, so now it's alpha MV1 is equal to alpha MV1 into OL1. Okay, so here OL represents the open loop binary variable. So if you keep this binary variable as 1, then you can say that it's just open loop, there's no control action, because you're just the RHS, the right hand side of the equation, is left hand side of the equation. Of course, once you give a binary variable as 1, automatically all other binary variables are turned to zeros. Okay, so or else if you want to run a closed loop simulation with proportional integral proportional controller, you can make the OL1 as 0, and then you can use the second part of the equation where you have P1 into error 1 into alpha MV1 star into CL P1. Okay, here CL is the closed loop and P represents the proportionality controller for the first pair of MV and CV. And similarly, if you see the second part, the next part of the equation, it's P1 into error 1 and I1 into AE1, which is nothing but your integral. Okay, and you have alpha MV star, MV1 star, and then you are multiplying it with CLPI1. Here it represents closed loop proportional integral 1 for pair 1. Okay, similarly you can write for PID also, and you can see there is one binary pair at the end which represents for pair 1. Okay, Similarly, if you have more than one pair, the equation has to be again written for other pairs also. So I told you, right? I mean, so here you can see the table where by just substituting different values for the binary variables, the same model can be used in ProCACD. Okay, for example, if the binary variables OL1 is set to 1 and all other binary variables are set to 0, then the model is just open loop simulation. And similarly, you can run closed loop simulations for PID, and PI type of controllers depending upon the variables. Okay, here as I told you, I mean the suffix 1 represents one set of MV and CV, and if the system has multiple inputs and outputs, the model has to be expanded correspondingly, including all the pairs available in the system. Okay, now let's go to the main problem. Let's try to see in the coming slides how the tool can be used for using the help of the generic model, how we can use for designing a controller, and also analyzing this controller, let's say for the same process. Okay, so in a control design or a controller design, there are three important steps that needs to be carried. First is controller pairing. Okay, in controller pairing, this is a very important step in processes where there are multiple manipulated and controller variables. Okay, so this is what it gives you, is it gives you the best pair in order to design a robust control system to the process. Okay, in this tool we take all the possible pairs of manipulated and control variables and generate what we call as a relative gain array. So this relative gain array gives the information about what is the best possible pair. Okay, so here the relative gains, okay, of the diagonal elements close to 1 and for off diagonal elements close to 0 indicate a very good selection of variables or a very good pair of MB and CB. Okay, and similarly a values close to 0.5 for off diagonal elements indicates a very strong interaction. We generally try to avoid such kind of pairing. So in general, if you look at an RGA matrix and if we see pairings which has the diagonal element close to 1, that means that pair is has the minimum interactions and is the best, and with respect to the process, it's the best pair to use in the control structure. Okay, and the second most important thing is the controller theorem. Okay, here ProCACD uses an online method where we submit. First, we try to generate the system response data by just giving a step input on all the different available manipulative variables. We just give a step input, and then we will record the response of the system in the form of the change in CV and how much time it took to go to a new steady state, etc., and all these things. Okay, so all this information is stored, first generated and stored, and this data is uploaded to TiGPID. So this is an online server which is also developed at JGU. Okay, and what it does is like it uses the data and it runs the system identification and tuning methods. Okay, and it will give you the transfer function which will represent the system and also the tuned controller parameters. Okay, and finally the third one is the performance analysis. Once the control parameters are tuned, you need to verify how are they performing, and for this we can use any analysis methods like disturbance rejection or set point tracking. So in disturbance rejection, what we try to do is we try to give a small disturbance and see how the controller is able to reject this disturbance and bring the control variable back to, or keep the control variable at the set point. And another analysis what we generally do is tracking of set point changes, where we try to arbitrarily change the set point and see how fast the controller was able to bring the control variable to the new set point. So based upon all this, we can easily tell whether the control structure and the tune parameters are robust or not. Okay, so let's see. Let's use the same example and see how to kind of come up with the controller design and how to analyze it. Okay, so as I told, this is how the interface of the ProCACD looks. Okay, and as I told, the first step is to develop a generic model. Okay, so for this example, I've used the same equations what I've showed you previously, and I've made a MOT file as a tank MOT. Okay, now you can browse this model directly to ProCACD, and you can see, and that's the first step. You need to have the model of the system. Of course, there's a library, and if you're lucky, you can also find the model which you are looking for. Since it's a generic model, you can always modify it to the needs of your own system. Okay, so once you browse the model, all the information from the model is extracted and filled accordingly. Okay, the second important thing is the user has to choose which type of control system are we looking at. Is it an open loop simulation or a closed loop simulation? So based upon this selection, it automatically chooses which binary variable has to be 1 and which binary variable has to be 0. Okay, so that's the second part. And in the third one, so here is where the suffixes in the generic model will be helpful. Okay, here both you can see it has already identified one manipulated variable and one control variable, and it also got the information what is that particular variable in the model. So in our case, it's alpha mv1 is the manipulated variable, and uh, the height is the control variable. And here the option is given to the user which one to choose. Here I chose for this example proportional integral controller. Okay, so once you choose this one, as I told, it automatically keeps the other controls structures like proportional controller or PID to zeros. All those binaries will be 0 and only this binary variable will be set to 1. Okay, now let's go and see the next step. Here in the next step, you can see the model variables on your left. What are the model variables? On your right, it also gives you the different information of the model. So how many parameters are present, how many known, how many explicit equations, and how many dependent primes and dependent variables are present, and what is your manipulated variables, and the list of the manipulated variables and control variables is also given on your right hand side. Okay, so that is just for viewing the model and model parameters in ProCACD. Okay, so in the next step is the controller tuning. Here you don't need to do the control pairing because we only have one pair, and of course I'll show you what would be the end result for RGA analysis for one MV and one CV would be 1, which is like the ideal case. Okay, so as I told, in the next step is the controller tuning, right? In the controller tuning, first thing is you need to generate the system response data. For that, you need to give the number of either the time period or the number of points you're looking at. Okay, once you have given that, you will click the generate data option there. So once you have clicked the generate data, what it does is like, so in this case, it has tried to give a step change on the manipulated variable alpha. Okay, and then it records the system response in with respect to the height of the liquid, which is our control variable. Okay, all this information is stored. Okay, once you have used the system identification step, right? So the system identification step, what it does is like it takes the data what you have generated, it submits all the information in a particular format to the server, the TIGPID server. Okay, so the TIGPID server will use this data to come up with the identification results and the controller parameter results. Okay, so the identification results you can see on the left side, where it gives the numerator denominator are nothing but the coefficients in the transfer function. Okay, and the tuned results are nothing but the parameters of the control structure, your proportionality constant and your integral constant. Okay, so the next step is, as I told, you also need to analyze or verify your controller performance. So for that, you will go to the next, which is the closed loop runs. Okay, here you can see there's a drop down. Here you can choose different types like disturbance rejection uh, or set point tracking. There's other options also. I will show you when I'm giving you the live demonstration. Okay, and also you can run single run or multiple runs to see how is the system is kind of behaving intermittently. Okay, so in this example what I did is like I gave a disturbance in the form of the inlet feed F in, where I've increased it from 0.1 to 0.25. Okay, so now you could clearly see, and then you should click run, and you could see a combined plot where the yellow line represents the change in the control variable, the height. So the moment I have released or I have increased the flow rate inside, going inside the tank, there is a sudden spike in the height of the tank, or the liquid height in the tank, which it went all the way beyond 1.5, and then slowly, because of the controller action, where it tried, you can see the blue line represents the alpha, the control valve, the valve opening, where it has slightly increased the valve opening, and then you can see the height was again brought to the original set point of 1. Okay, so that is one type of analysis, and you could see the control variable was brought back to the set point by just opening the valve. Okay, now the second type, as I told, is the set point tracking. So here what I did is like I have changed, the original set point was 1, right? So now what I did is like I have changed the set point to a 1.5, and then I click run. So here you can see the yellow line, the yellow represents the set point change, and of the control variable, yes, and the blue line represents the valve opening, which it is trying to adjust so that the new set point was maintained, where the new set point is maintained with respect to the control variable. You can clearly see that it's kind of performing very well with respect to both uh, disturbance rejection and set point tracking. Okay, now what are the other types of problems this tool can solve? Okay, I mean, you are aware of the fact that uh, it is very important to uh, design both the process and the control structure together, because in most of the cases, I mean, in general, what they do is like they try to design the process first, and then, and based upon these design parameters, they come up with this kind of control structure um, which fits the original design. But then in most of the cases, this is this is not a very optimized way of getting both the process design and the control structure. So it is advantages to do an integrated process and control design. So that type of integrated problems can also be solved using ProCACD. Okay, so here I'll just give you the example and I will show you the solution approach only. Okay, here let's say there is a reactor. In the reactor there is a fresh feed coming in, which the feed is at a temperature, let's say TF, and the feed has two chemicals, let's say CeO and CW, which is like ethylene oxide and let's say water. In the reactor should be maintained at a particular temperature, okay, which is T. Okay, for this you will maintain a cooling medium and you will maintain the reactor temperature by regulating the flow rate of the cooling medium. Okay, at the end what you get is of course some unreacted raw materials and three products in the form of EG, DEG and TEG. Okay, now what would be an integrated design control problem here? Here the most important design parameter for this is the volume of the reactor, because the capital cost of will be highly dependent on the volume of the reactor. Okay, and of course you also have a manipulated variable in the form of FC, which is the flow rate of the cooling medium, and here you need to control the composition of the products by maintaining a certain temperature in the reactor, which is T. Okay, so this is an integrated design control problem. So traditionally what they used to do is like they used to first come up with the design variable VR, which is the volume of the reactor, and then they try to come up with the structure, and also the controller parameters are tuned for the original design variable. Okay, but that's not an optimized way of doing it. So for that, what we can propose is an integrated design control approach. Here you have a process model first, which is the reactor model. So you'll configure a closed loop simulation in a generic format. Okay, and then in the cost function you will take the design parameter VR and you will have a cost function which will take VR as an input, and then you will take the performance metrics, okay, which will include the controller factor. For example, ITSE, it's a controller, it's just the square root error, okay, of your set point and your CV. So the error, so based upon these two, like the cost function and the performance matrix, you will come up with an objective function so that it has representations from both the process design and also it has representations from the controller design. So in that way you will calculate your objective function, and then you can use any derivative free based optimizer in the outer loop. So what you do is you send this objective function values into the optimizer, and based upon this the optimizer will give you a new set of design variables and controller parameters which will be sent to the process model. Again you run the process model in MOT, and again you calculate the cost function and the performance metrics and then the objective function, and this cycle will go on until you get an optimized objective function which will give you the best PR or the design variable and the best controller parameters, the best proportionality constant, best integral constant, etc. Okay, so this also has been implemented, but we are right now in a testing phase of this thing. So now we can go for a break But after the break, I will show you a live demonstration of the previous example. We will try to develop it and see how this can be solved in ProCACD. Okay.